Well, welcome to Topic 7, Random Variables. We're going to understand the concepts of a random variable and distinguish between discrete and continuous random variables. Find the probability distribution function of a discrete random variable and use it to find probabilities. And to find the mean and variance of a discrete random variable and apply these concepts to solving real-world problems. So we'll be looking at a random variable. We'll be focusing on the discrete random variable. And we're going to calculate the mean of a discrete random variable and the standard deviation of a discrete random variable. So there are two main types of random variables, discrete and continuous. Now, a random variable that has a finite or countable list of possible outcomes with probabilities assigned to each of these outcomes is called discrete. A random variable that can take on any value in an interval with probabilities given as areas under the density curve are continuous. Very much, if you think about it, when we talked about variables. So a discrete random variable will be things like number of pets owned, so you can count them. Numerical day of the month, 1, 2, 3, 4, all the way to 31. How many days of class was missed? All of those can be counted. And this is a discrete random variable when the values of the variable can be counted. A continuous random variable is often measurements. So the variable and the values would be something that would be measured, like weight, temperature, time it takes to travel to work. So anything that you would need, a stopwatch, a ruler, a speedometer, anything like that to get the value, that would be a continuous random variable. Now, looking back when we were talking about probability and probability models, remember that a probability model is a mathematical description of long-run regularity, consisting of a sample space and a way of assigning probabilities to each of the events. So in just 2 or 3 brief looks at a situation, we might not see that long-run regularity, such as flipping the coin. If I flip it 3 times, I could see heads 3 times, and you would go, but I thought it was a 50-50 chance. In the long run it is. In the short run, not always so true. The discrete probability model of a discrete random variable, we write it with that capital X, relates the values of X with their corresponding probabilities. And we call it discrete probability distribution. Now the distribution or model could be in the form of a table, in the form of a graph like a histogram or would be a histogram, or in the form of a mathematical formula. So notationally, if X, capital X, is a discrete random variable and little x is the possible values for that discrete random variable, then we would write it as the probability, and in parentheses, capital X equals small x, as the probability X equals to that value, little x. So here's some examples. If I'm tossing a coin and X is the number of heads that I see when I toss the coin, well, the probability that X equals 0, that I see 0 heads on a toss, I've got a 50% chance, a 0.5 probability of that occurring. The probability that the number of heads that I see, which is what my random variable is, would be 1. That means I see 1 head. I've got a probability of 0.5. In another example, in rolling 1 die, if X is the number rolled, then the probability that X equal 1, that I roll the die and get a 1, I have a 1 in 6 chance of that occurring. So let's look closer at that first example. In tossing 1 coin, if X is the number of heads, then the probability X equals 0 is 0.5, and the probability X equal 1 equals 0.1. That is, we defined X, our random variable, as the number of heads when we toss 1 coin. So this is how our model would look in table form. X equaling little x. That means these values in this column right here are the values that our random variable, number of heads when we toss 1 coin, can take on. It can take on the value of 0 and the value of 1. Now the probability that I get a 0, in other words, seeing no heads, is 50%, and that's what this symbol means. In place of the little x, I put in 0, and that would be 0.5. That's how we read the table. And the probability x equal 1 is 0.5. Now, if I were to make a histogram of this with the values of 0 and 1, well, my bars for this would both be at 0.5. Ooh, let me make this a little bit better. Sorry about that. Would both be at 0.5, be a uniform distribution. Now let's look at another example. In tossing 2 coins, if x is the number of heads, well, now we have to think about all the different outcomes. And if I tossed a coin, 2 coins, I could either see 2 heads, or I could see the first coin having a head and the second one having a tail, or the first one having a tail, the second one having a head, which is this one right here, and then no heads at all. So I have 4 separate outcomes for this particular experiment. So, how many times did we see 0 heads? Well, we only saw that 1 out of the 4 different outcomes. So, we saw 0 heads only 1 time. So we get 1 out of 4 as its probability. How many times did we see just 1 head? We saw it here and we saw it here. So 2 out of the 4 times, that's the probability of tossing 2 coins and seeing only 1 head. That were both of these right here. And how many times, or what would be the probability of seeing 2 heads? Well, we saw 2 heads only 1 out of the 4 times. And that's how we got our probability model. And we could put it on the number line. So here we could make a histogram of it in graphical form. So here's 1/4 and 2/4. So we saw it 1/4 at 0, 2/4 we saw at least 1 head, we saw 1 head, and then we saw 2 heads only 1 out of the 4 times. Now, discrete probability models must satisfy these 2 probability rules, that the probabilities have to be numbers between 0 and 1, and that the probability, when you add all of them up, all of these probabilities for the different values of x's, they have to equal 1. That's how we know that a probability distribution is a true discrete probability model or distribution. So, look at this discrete probability model or distribution and decide, is it a probability model or distribution? Well, in looking at it, all these numbers are numbers between 0 and 1, including 0 and 1. They all are between there. And when I add them all up, they equal 1. So both of these are satisfied. Therefore, this is a discrete probability distribution. Let's look at another example. Is this a discrete probability distribution? Well, upon first look, you can see it's a negative number. So right away, we know this cannot be a discrete probability distribution. But even if we added up all these numbers, they don't equal 1. So therefore, it had all kinds of problems. Now let's look at another example. This is a probability model. And we're going to look at rolling 2 fair die, a 6-sided die, one that's red and one that's green. And we can actually pictorially show all the outcomes. And there's 36 different outcomes in here. And if our random variable is the number, after we roll the dice, the number that we get, or the number of pips that we see, this one would be x equal 2. This would be x equal 3. This would be x equal 4, and so forth. So we could say, what's the probability x equal 2? Well, we only see that 1 out of 36 of these outcomes, so the probability of rolling a 2 is 1 in 36. The probability of rolling a 3, well, these are the only 2 ways to get a 3, so the probability of rolling a 3 is 2 out of 36. Why could I say that? Is because these dice are failed, so we have each outcome is equally likely, so we have a 1 in 36 chance. So here's one way to roll a 3, another way to roll a 3, so there's where the 2 out of 36 comes in. So we could actually take our sample space and make a chart or a table of it. So there's the 2, the 1 out of 36, 3, 2 out of 36, 4, 3 out of 36. So again, putting it together, seeing 4, how many different ways I could roll a 4? There were only 3 ways I could roll a 4, and that's why I have a 3 in 36 chance of rolling a 4. How many ways to roll a 7? Where that's the most I could have. And there's 6 of those. 6 out of the 36 chance of rolling a 7, and so forth. So I could use this table to find probabilities. So now it's your turn. I want you to find what is the probability of rolling at least a 9, what is the probability of rolling no more than a 4, and what's the probability of rolling a 13. Well, here we go. Rolling at least a 9, that would mean we'd have to add up all of these, and we get the 10 out of 36. Rolling no more than a 4, that means 2, 3, and 4. So I add up these 3, and I get 6 out of 36. What's the probability of 13? Well, that's easy. We can't do it. So the answer to that is 0. Finding the mean of a discrete probability distribution. Well, we take the variable value times the probability that it occurs, and we do that for each of the different random variable values. And then we add up these products, and that would give us the mean, or the expected value of our discrete random variable. So now it's time for you to find the mean of this discrete probability distribution. So when we do that, again, we just take the variable value, multiply it by its probability, and we do that for each of the variable values. We take those products, and then we add them, and so the mean of this distribution is 2.5. The expected value for our random variable is 2.5. And as you can see, 2 has a huge probability of occurring. It's weighted high. So we should have seen that our mean should be somewhere near 2. Just like with your weighted averages for your grade for the different pieces of our class. So if 70% of your grade comes from tests, that's what you want to concentrate and do well on. In other words, it will affect what your class average will be because it is weighted greater. How can X bar be an accurate estimate of mu? How is that possible? Well, after all, different random samples, as we know, will give us different values of X bar. But if we keep taking larger and larger samples, the statistics that X bar is guaranteed to get closer and closer to the parameter U. And why? By the law of large numbers. It says that as the number of observations drawn increases, in other words, the number of times we do something, we do it more and more, the sample mean of the observed values get closer and closer to the mean of the population. And remember, mu is just the symbol for the mean population. Now, how do we find the variance and standard deviation of our random variable? Well, we have to take each of the random variable values, square it, multiply it by its probability. We do that for each of the values, we add them, and then we would get the variance. To get the standard deviation, we just take the square root of the variance is our population standard deviation. So now it's time for you to work. Let's find the standard deviation of the probability distribution we've been working on. So we look in here and we take each of our data values, we subtract it from the mean, that's what we have here. We square the value and multiply by its probability. We do that for each of the variable values, sum them, and we get 2.45. So 2.45 is the variance of this distribution. To get the standard deviation, we take the square root of that. And so rounded to 2 decimal places, we would say our standard deviation is 1.56. So we've looked at random variables, discrete random variables, the mean and standard deviation of our discrete random variable. Thanks so much for watching.